You put two computers in a room together and give them a shared collaborative task where they need to communicate. Can they learn to communicate? Can they learn to collaborate? So that's what we're going to talk about. So the computers are going to start off with no knowledge of language. They're not even going to be able to see. They don't know anything about each other. They certainly don't know the same language. And they're going to have to somehow collaborate together, come up with a language that they both understand in order to solve the task. And they're going to do this without using any communication other than this language that they don't actually speak yet. So can they do that? This field of investigation has a technical name, which is emergent communication. And I want to talk about a particular research paper by Angeliki Lazaridou, which investigates this question for images. We're going to give an image to the first computer. The computer is going to say something to the second computer, and then the second computer is going to have to choose the correct image, the original image, from among some distractors. So the second computer sees maybe 3 or 4 images, 3 or 4 pictures, and has to choose the correct image. We're going to call the first computer the speaker, and we're going to call it a model rather than a computer. We can actually run multiple models on the same computer. I might also sometimes call it an agent. So we have 2 agents or 2 models, and we have a listener agent or a listener model. This type of task also has a technical term. It's called a referential task. I'm interested in these types of tasks because it combines 2 areas that I'm interested in. It combines something called reinforcement learning, which is how AlphaGo, AlphaZero, the OpenAI 5 for League of Legends, like all of these things work using reinforcement learning. The Atari games that was from DeepMind, that was also using reinforcement learning. So the emergent communications, getting the computers to learn to talk with each other, this also uses reinforcement learning. And I'm also interested in it because it's using natural language processing, which is something I use a lot at work. Yeah, so we have 2 computers or models or agents, and they're going to have to collaborate. But so in this diagram, they've actually got a language, but actually they don't start off with a language. They just can say random stuff to start with, and they're going to have to learn to understand each other by saying random stuff. So if the speaker says something random long enough, but it's not random, like the speaker consistently says the same thing to mean the same thing. So if the speaker says ADXF whenever the speaker sees a red sphere, then the listener can gradually learn, okay, ADXF means red sphere. But this is going to take a long time, but we will see that they can do this. Here's the title of the paper. So it's called Emergence of Linguistic Communication from Referential Games with Symbolic and Pixel Input. We're not going to talk about symbolic input. Symbolic input is much easier than pixel input. Pixel input means like images. In this case, 3D objects. And so the first author is Angeliki Lazaridou from DeepMind. And this was published as a conference paper at iClear, which is one of the, in my opinion, it's the main conference for reinforcement learning. There's lots of papers by OpenAI and DeepMind at this conference. Okay, so here's the task, the referential task. So we've got this target image. So in this case, we've got, it's like a sort of pink sphere. And it's sitting on a floor, but the floor is just there to distract the agents. All that matters is the color and the shape of the object. But the agents don't know that. They just see these pictures. And so this is given to the speaker agent. So I'm using like agent and model sort of interchangeably. And so then the speaker sees this object and then has to say something, which is going to be like a sequence of numbers. You can think of these numbers as letters. So like 22 would be like the 22nd letter, and 2 would be like B is the second letter, right? Well, I guess if it's starting from 0, because the third one is 0, so that would be A, and then 2 would be C, and then 22 would be like Y. But we're using numbers because actually the alphabet is not, the models are not limited to using just 26 letters. They can use about something like 100 different possible symbols or letters. Then the listener receives this utterance, this 2220, the listener can't see which is the target object. The listener sees 3 pictures. Now the listener doesn't know which pictures are distractor pictures and which picture is the actual target picture. The listener just sees 3 pictures, and then the listener has to pick out the right picture based on what the speaker said. So, and this is the referential task. Right, and then a question is, can they solve this task? Well, yes, they can actually. Angeliki found that they got a test accuracy of 94%. So she trained them on lots and lots of different objects, like different colors, different shapes, different positions, mixed together with other objects as distractors. And then she tested them on some new objects that they'd never seen, and 94% of the time they could solve the task. So when she tested them, she stops them learning, she freezes them, and then she gives them some new objects that they've never seen, and then finds out like what accuracy do they get on those objects. So 94% of the time they are able to communicate with each other sufficiently to solve this task, which is pretty impressive really, because they're starting from nothing, they're starting from no language. So then a question is, what does the language look like? So in the paper, Angeliki presents some examples. And so here's a language where the model can communicate, can send 2 symbols at a time. So basically like 2 letters. Each symbol is from like 0 to 100. And so here the message prefix is the first symbol and the message suffix is the second symbol. And then what we can do is we can look at examples of target images that correspond to each of these messages. So here, this is the message that's sent by the sender, and the images we're going to look at are some of the images that were given to the sender and caused the sender to give this message. So starting with 30. So here we've got some sort of red oblong somewhere near the bottom left. And then here we've got a yellow oblong-y thing also near the bottom left. And then here we've got a green kind of oval thing also near the bottom left. So clearly these are all different colors, and they're not really, they're kind of similar in shape, like they're all kind of roundish, but they're different. But what do these all have in common? Well, they're all in the same position, right? They're all towards the bottom left. Okay, so maybe this message is sending something about position. And then here's a different message. So this is 3:30. And we can see now it's on the left, but a little bit higher up, and it's yellow, and it's a sphere. Here's another one for the 3:30. It's still a sphere, but now it's red, so probably not. It might not be communicating color, but it's in the same position, right? So this corresponds to our previous hypothesis that maybe it's communicating position. And then a green, different color, cylinder, different shape, but the same position. So it basically looks like the agents are communicating position. So, and then here we've got, again, they're all different shapes and colors, but the same position as each other. And if we look, the objects with a suffix of 0, they're both kind of the same location up and down, but the prefix of 5 versus 3 is sort of shifting where they are, like horizontally, right? And then we've got 5 and 30. So now basically the up and down is the same as the 3 and 30. So it looks like the 30 is the second number, the suffix is representing like how far up or down. And then, but the 5 is different position horizontally than the 0. So basically one of these numbers is being used to represent the x, and one of these numbers is being used to represent the y. So that's kind of interesting. But so in this case, the receiver, the listener, is being given 20 distractors. So this means that the models have to work pretty hard. If the speaker doesn't give really accurate information in its utterance, the listener's not going to be able to pick the right answer because there's 20 distractors. So 20 distractors, there's like a 5% chance of getting it right by chance and a 95% chance of getting it wrong. So they're going to have to work really hard. And so in this case, because the models are kind of lazy, but in this case the models have to work really hard, they can't be lazy, so they learn to communicate the position using the message. But like, here's another example. Here we only have 2 distractors, and now look. So here is a message 1 0, and it's all over the place. They're not the same position, they're not the same color, they're not the same shape. Here's a different message 0, and again it's all over the place, and different message 530, and it's all over the place. So in this case of 2 distractors, when there's only 2 distractors, the models seem to be kind of lazy, and they're not really like communicating things in nearly as detailed a fashion, or as not nearly as clearly as in the 20 distractor case. How can we stop the models being quite so lazy? So one thing we can do is, why don't we change the viewpoint? So instead of giving the exact same image to the listener that we give to the speaker, we're going to give a different viewpoint of the same image. So here you can see we've got the same floor pattern, we've got the same color, we've got the same shape, but we're not seeing it in the same from the same viewpoint. And so what happens here? So the paper doesn't actually give any data for this experiment, unfortunately. It gives the overall result, but not not any examples. So I have to confess, I made this example up, this data up. So the overall result matches the paper, but this actual result I made up for the purposes of this presentation. So here what happens is, right now the speaker's not really caring about position anymore. It's basically caring about color. So basically so here we've got 2 distractors. So by chance the speaker can get the right answer like a third of the time, because there's 2 distractors, there's 3 pictures in total. So if the speaker communicated the position somehow, then the listener before was able to get the right answer, but now because we're changing the viewpoint, the listener can no longer get the right answer from the position. So the speaker's forced to change its strategy. And what the speaker's doing is it's basically using the color. It's sending the color to communicate which is the right object. And so here's a different message, and then like here we've got the color white, and then here's a different message, and here we've got the color yellow. Right, and then okay, so we are able to get these agents to learn to communicate. So you put them in a room together, you give them a shared task, and they're able to learn to see, and they're able to learn to communicate. But how can we create such agents? Like, if we wanted to run this experiment ourselves, how would we do that? So let's first describe the sender agent. So we're going to have an image that's going to come in. So over here, let's have an image, and this could be like, say, a red cube or something like that, let's say. So here we've got the red cube. So this is an image. And then we're going to give that image to a vision module. So here we've got a vision module, and that's going to be a CNN. But so let's just write vision. And this is going to be a CNN. So a CNN is a convolutional neural network. It's a standard brick in machine learning. So it takes in an image as its input, and as its output it's going to give some sort of representation, basically a bunch of numbers or a thought vector. You can think of it as representing somehow the image that was given to it. And then the output of the visual module, the CNN, we're going to give that to a language module, which is an LSTM, which stands for long-term short-term memory, which was invented by Schmidt a while ago. So this is going to be the language module. And as we say, this is an LSTM. So again, this is a standard block in machine learning. If you pick up any machine learning library like TensorFlow or PyTorch, it contains an LSTM and it contains CNN modules. And then the output of this language layer is then going to be like some language, some letters, some whatever we want to, however we want to think about this. So some tokens, some letters, some language. And so what we're looking at here, this is the speaker. So the speaker takes in an image, gives that to a vision module, which gets a representation of what the speaker's seeing, and then takes the output of the vision module, gives it to a language module, which then is converted to letters. So the speaker overall takes an image, and from putting it through these modules generates letters, which are then sent to the receiver. Alright, so we've presented the speaker, how the speaker works, and then we should also go over how the receiver works. I guess we can just copy and paste some of this stuff. So the receiver is also going to receive an image, actually several images. Like that. So let's just paste that in. And so the result, so in the case of the receiver, we don't give the vision output to a language module. We simply keep this representation, and we're going to compare it with the representation that we get from the language module. So, well, let's add in the language module. So in the case of the receiver, we're going to get multiple images. Here we're just showing one image, but we're going to have 2 or 20 other images. And we're also going to get some language. So let's draw in the language. So we receive some well, I can copy it, I guess. We receive some letters. And we're going to give these letters to a language module. So we're going to take this language module and we'll just copy that into here. Okay, so then we've got, so this is for the receiver. So the receiver takes in an image, encodes that, and let's say it encodes that into some, it encodes that into some thought vector. So we can represent that thought vector here. So here we've got a thought vector that represents what the receiver is looking at. And we also have another thought vector which represents the words that the receiver, the characters that the receiver received from the sender. What the receiver is going to do is compare these two thought vectors. So is this going to be like there's a mathematical operation called a dot product. It's just a standard mathematical operation. It's also included in every machine learning, well, in every like deep learning library like PyTorch and TensorFlow. So you simply give it like 2 numerical representations, and it's going to give you a number between. It depends on how you do it, but like typically between -1 and 1, and if it's near 1, then it's the 2 vectors are similar, and if it's near -1, they're dissimilar. There's a little bit more nuance around that, but generally, like approximately, that's how the dot product works. So basically, the dot product, the more positive it is, the more similar the vectors are, and the more negative it is, the more different they are. And so the receiver receives a single utterance from the speaker, and then the game gives the receiver several images, like maybe 3 images, maybe 21 images, and the receiver is going to compare each of those images with the language received from the sender. How they're going to do that is the receiver is going to take each image, pass it to the vision module, the CNN, to get a thought vector, and then compare that thought vector for that image with the thought vector from the utterance received from the sender. Whichever image has a thought vector with the highest similarity with the language thought vector, that's the image that the receiver is going to choose, and that's what happens. All right, and then here is, so you've just seen the pencil sketch version, and then here I've made some slides showing the same thing, but a little bit neater than my writing. So we've got an image, comes into a vision module, goes to a language module. This is for the speaker, and then that language module is going to generate an utterance. And then on the listener, we take each image, pass it through a vision module, we get a thought vector. We take the utterance that we received from the sender, send it through a language module, get another thought vector, and then we're going to compare those two thought vectors, and we get some sort of a number that represents how similar that image is to that utterance. And the listener's going to do that for each of the images that the listener receives, and the listener's going to choose the image which has the highest similarity with the language sent by the speaker. Okay, so that's how the models look. But then how do we train them? How do we teach these models? So what we're going to use something called reinforcement learning. So reinforcement learning is we're going to give a reward to the agents when they get the right answer. So from a big picture, we've got this image, goes to the speaker says something, the listener sees its images, says which one it is. Right, and now what happens is we're going to give it a reward. So if he gets it right, we're going to give a reward of +1. And we're going to give that reward to both of these agents. And what happens is, when the agents get a reward, because it's called a reinforcement learning, right? So when they get a reward, the reward reinforces what they just did. So whatever they just did, they're going to learn, okay, we should do that more. And if they get like a 0 reward or a negative reward, then they learn, okay, whatever we just did, we should do something different in the future. And each time that they do this experiment, each time they run a single example, which can run very quickly, each time they run a single example, they learn a little bit. And then what happens is we get them to just play this game over and over again, like millions of times. This can take several days, but we don't have to do anything ourselves. We just click run or run the script or whatever, and it's just going to go away and train these models for several days. That might sound like a long time, but if you think about a newborn human baby, newborn human baby takes maybe months to learn to see and to speak. So a few days is not bad. But I mean, of course, the newborn human baby learns to see and speak quite well, whereas these models are giving quite rudimentary communication for now, but still they do succeed in learning to speak with each other using reinforcement learning. Now, this is a hard task for them to learn, because the thing is, as the speaker learns, the speaker's going to give different utterances, and then so the listener's also learning at the same time. So the listeners gradually learn, okay, 2220, maybe that means like a pink sphere. But then the speaker maybe changes as it learns. So it changes, so it's no longer using 2220 to use it to be a pink sphere. It might use 2420 or something like that. And so now the listener has gradually learned, okay, 2220 is a pink sphere, but now it has to relearn it, and now it's 2420. So both the speaker and the listener are changing at the same time. So it doesn't always converge. It's a challenging task. It's an unstable task. It doesn't always converge, but usually they manage to converge and learn together. Sometimes it doesn't. But it takes a long time, like millions of gameplays. All right, so we've talked about how these models look. Like, how do we design these models? How do we train these models? Now, initially, these models are completely blank slate. kind of like a newborn baby might not be able to see, might not be able to talk. I mean, they definitely can't talk. Can they see? Unclear. But like one can imagine, it might take a while for the newborn baby to learn to see, and clearly it takes them a while to learn to talk. And our models are no exception. When we first create the model, you can create these models in a few lines of code. Okay, here's my convolutional neural network. Here's my LSTM, and you just give them a dimension. Like, okay, I'm going to have a convolutional neural network with like 3 layers, and each layer has a kernel which is 3 by 3, and we're going to have like 16 feature planes. So, I mean, this might sound like kind of jargony, and it is, but you basically just give it a few numbers, like maybe 4 or 5 numbers, that defines your convolutional neural network. But that convolutional neural network won't do anything useful yet. Like you can give it an input, it'll give you an output, but that output, it will basically be random, and you have to train it using the reinforcement learning for a long time before the visual module can actually do something useful, before the convolutional neural network gives some useful output. And it's unclear what it's learning. And a question is, when we train these modules on this task, what does the visual module learn? And what we'll see is that in some of these experiments, the visual module is colorblind. It can't see color. Sometimes it can't see shape. It does tend to low position quite well. So in a lot of these experiments, the sender completely ignores the color because the visual module doesn't see the color. It might ignore the shape, and it basically can just see the position. And it depends on the task that we give it. According to the task that we give it, the models will learn, their vision systems will learn something different. So then the question is, how can we tell what their visual systems can perceive, can see? And what we do is we're going to use something called a probing model. How does a probing model work? So we've got our image coming in. So let's draw a cube. Right, and then this is going to go to the vision module. So this is the vision. Right, and what we want to this is from the, well, this can be from either the speaker or the receiver, but I'm particularly thinking about the speaker for now. And in the paper, in Lazarudi's paper, she's experimenting on the speaker's vision module. So how can we find out what this vision module has learned or can see or can recognize or perceive? So what we do is we're going to send the output of this vision model to another machine learning model, which we call the probing model. So we take this output and we send that to a probing model, and we can create different probing models because we can probe for different things. And what we're going to do is we're going to train this probing model. We're going to fix the vision module so the vision module doesn't change, like whatever it. So we run the experiment like the main experiment where we're getting the agents to be able to identify the appropriate picture, like the appropriate object. Once we've done that, so we've run that millions of times and the agents have learned, then we're going to freeze the vision module. So the vision module is not going to learn anymore. And then we're going to attach this probing model to the vision model. And then we're going to train the probing model to predict something. So it can predict, for example, color. All right. Now, let's imagine that the vision module is colorblind. It can't see color. So the output of the vision module is basically a representation of like other things that the agent can see. So the position, for example, or possibly the shape, but it won't contain any information about color. Now, if we train a model, this probing model, to predict color, and the input to the probing model is the output of the vision module, if the vision module has not learned to recognize, to somehow represent color, we're not going to be able to train this probing model. It's going to give a really poor accuracy. Like well, it might not be 0% because let's say there's 5 colors, so it might be like 20% or something. So if it gets 20%, then the visual module doesn't contain any information about color. If it gets 100%, then okay, the vision module clearly is able to see color. And then, like, depending on what the actual number is, like maybe the actual number is 70%. So okay, so it can sort of perceive color. So this is a probing model, and we can probe for different things. So we can have different probing models. So we could have another model, and this one's going to try to predict the shape, for example. And we can have another one which can predict the position, for example. All right, so that's probing models. So that's what the probing models do. That's how they work. These models are trained supervised. So supervised training, input and output. These models are very easy and quick to train compared to reinforcement learning models, which are super slow and very unstable. Especially in these particular emergent communication experiments, the reinforcement learning is very unstable because you've got both the speaker and the listener learning at the same time, so it's incredibly unstable. But these probing models, these are supervised learning, very fast, very easy, very standard, very well understood. So if you can train the probing model to recognize the color, then the vision module can see color. And if you can't, if the probing model is unable to predict the color, then the vision module it's very unlikely to contain any information about color. So this is how the probing models work. All right, and then so you've just seen a pencil version of probing models, and then here's like a nice, neat version of the same diagram. So we've got the image coming into the vision module, and then we've got different probing models, and then like we've got one probing model to predict the color, one to predict the shape, and one to predict the position. Oh yeah, so one clarification on how the supervised learning is working. So what we're doing is we're going to take like lots of different pictures. One at a time, we're going to give a picture to the vision module, and then we're going to check so the picture could be like a blue sphere, let's say, and then we're going to see, can the probing model predict, for example, the color? And we're going to do that many, many times for different objects. So we're going to give it like a green cube and a blue sphere and a red oblong shape, whatever. And then basically like on all of these examples, so let's say we train it on lots of examples, and then after we're going to see how it does on some test examples that it hasn't seen previously. So that's how we train the probing models, and that's how we test the probing models. All right, so here's the results of the probing models for some of the experiments that Lazarou did. So what we've got here is we've got a table. In the left-hand column, we've got the experiments. So we're going to show the results for 3 different experiments. And then we've got the probing model accuracy for the position and for the shape and the color. So what do we find? Like, what can the speaker's visual modules see? What does it perceive? So we're going to start with the first experiment. So this is 20 distractors. So we saw for the 20 distractor experiment before, we saw examples of messages, and we saw that the speaker was basically sending the position in the message. Wasn't really paying attention to color, wasn't really paying attention to shape. But what does the speaker's vision module actually perceive? So probing model of position, 95% accuracy. So clearly the speaker's vision module is very good. It contains very clear information on the position. The speaker's vision module knows exactly where the object is, and it passes that information on to the language model, to the LSTM. So what about shape? So shape actually also gets really good accuracy, like 90%. Not quite as good a position, but it's pretty high. I mean, by chance, like if the model just guesses, then the probing model would get like 20%. So 90% is really good. So the speaker's vision module can see the shape of the object and can see the position. What about color? Well, color is only getting 25%. Now, if the model just guessed, there's like 8 different colors here. So if the model just guesses, it's going to get 12%. So it's basically near chance. So basically we can consider that the vision module is colorblind. It can't really see color, or barely any color at all. Maybe it kind of like 2 different colors maybe. But it can see the shape and it can see the position. Okay, so that's interesting. What about if we do fewer distractors? So let's say we have 2 distractors. So in this case, position, the vision module can still see position, but not quite as well. So remember in the 2 distractor case, we saw that the language was, it was not really clear what it was describing. So in the 20 distractor case, it described the position really clearly. Like we could see we had the message suffix and the message prefix. And then in the 2 distractor case, it was a lot less clear what was being described. And if you took the exact same message and you took examples with the exact same message, they had different colors, different shapes, and different positions. All right, but we can see here that the visual module can still perceive the position of the objects, just not quite as well as in the 20 distractor case. But it can't really perceive their shape, like 41% compared to 90%. So when there's only 2 distractors, then the visual module doesn't really learn to see shape. It learns to see the position, but it doesn't really learn to see the shape. And what about color? Color 64%. So it's not great, but it's better than in the 20 distractor case. So it's interesting because according to how we train this experiment, according to the exact setup of the experiment, like how many distractors, then the visual module will learn different things. Like it's not always learning to see color, it's not always learning to see shape, it's not always learning to see position. What about if we change the viewpoint? Now we saw that when we changed the viewpoint, the speaker's messages were really clearly about color. It was just like, okay, this is a red object. So this is 2 distractors and change the viewpoint. And because there's only 2 distractors, it's enough for the speaker to give the color of the object in order for the listener to have a high probability of being able to choose the right object. So we might expect that here the color would have a higher percentage. Let's see what happens. So the position has gone down slightly, which makes sense because we're changing the position now between the speaker and the receiver. But actually, surprisingly, it doesn't go down by much. Like that's surprising. Like I would have expected it to go down, like almost a chance, but it's actually staying high. So the speaker's language module is only giving the color, but that language module is actually receiving information about the position. It's just not using it; it's throwing it away. Shape 44%. It's slightly better, but not much. So again, the language model is receiving almost the same information. It's just choosing to use different information, and color also very similar. So this is interesting. So actually changing the viewpoint hasn't actually changed the visual module much in this case, but changing the number of distractors did change what the visual module learns to perceive quite a lot. And in the 20 distractor case, the vision module is basically colorblind. It can't see color. It can see shape and it can see position, but it completely ignores the color. And then in the 2 distractor case, then it does learn to see color and shape quite well. Yeah, so this paper is interesting. Basically, if you put 2 computers into a room together with a collaborative task, and they initially don't have any language, and you just train them by giving them a reward whenever they complete the task, they will actually learn, and they will learn to communicate. Under certain circumstances, the language that they create will be sort of interpretable to us. We can see, okay, it's choosing the position or it's communicating the color. And at the same time, they're learning to see. So they have a vision module, which works a lot like the vision module in our head. Actually, at the back of our head, we've got like this layered system, which works a lot like a convolutional neural network. And through doing this task, they can train their vision system. They can learn to see. But they don't necessarily see everything perfectly. They might not see color, they might not see shape, they might see position better than everything else. So yeah, so the models are kind of lazy. The language that they learn, they sort of learn the minimum language to do the task. If we want them to learn some more fancier, complicated language, we probably need to give them harder tasks. Okay, and so that's the direction that some of the future experiments go in. Like we give them harder tasks, more challenging tasks, and when we see what happens.